Okay, so let's go over some problem types that are going to be on the test, and what sections they come from. So, yeah, I mean, first of all, the test is going to have 10 questions on it, and I'm showing you a total of 9 types of problems. So, in some sense, I'm basically telling you what's going to be on the test. Of course, the details are going to be different. You know, just because you know how to do one example of this type doesn't mean that you should be confident about all of them. Like you should try several of them. But in broad terms, I am basically telling you what's going to be on the test. I'm telling you there's going to be one like this, there's going to be one like that, and so on. So yeah, let me go down the list. So this test goes over kind of a lot of material. It's been kind of a while since we had a test. So the first material that this test goes over is like early chapter 3 when we were barely learning to take derivatives. So there might be a question where I just ask you to take the derivative of a function and maybe evaluate it somewhere, like given this function x squared sine x, find f prime of pi. So you just have to take the derivative and then plug in pi. So yeah, and that's covering several sections. That's 3.1 through 3.4, because that's like one section we learned product rule and quotient rule, and then the next section we learned chain rule, and so that's kind of a lot of sections that go into just knowing how to take derivatives. Anyway, let me move on. Then there's implicit differentiation. That's in section 3.5. That's like one like this, where you find y prime. You have to take the derivative, and when you take the derivative, remember there's y primes that show up in certain places, and then you have to solve for y prime. Then there's logarithmic differentiation. That shows up in chapter 3 in section 3.6. And these are ones where you learn to take the derivative of kind of crazy looking complicated functions, like maybe this, and also maybe this, where you have variables in the base and also in the exponent. These are the ones where you do the logarithm first. You write y equals this, and then you write ln y equals ln of this, and then you use log rules to simplify everything, and then you take the derivative. And so maybe that jogs your memory of what you're supposed to do for logarithmic differentiation. Yeah, so I'm just going over the general problem types and trying to give you at least a general reminder of what you do for each one. There's related rates problems. Those are word problems that involve a lot of detail, so I didn't write a specific example. If you want to see a specific example of these, they're in the book. You can look at these. But these are the word problems where everything is moving, everything is changing, and you have to find you do derivatives with respect to t. So you have d whatever over dt, and then you have to find all this information that's valid at the instant in question. It's those ones. There's then this type of problem out of 4.1. This is the ones where you just have a function in a closed interval, and you want to find absolute maximum and minimum values. So this one has a very straightforward procedure. You want to find the critical numbers. That means you take the derivative of this function, you find where it's 0, you find where it's undefined, and then in the end you just plug in all of those critical numbers and these endpoints into the original function, and whichever one's biggest is the absolute max, and whichever one's smallest is the absolute min. So that's these. Then there's questions that involve various information about the graph of a function, like whether it's increasing or decreasing, concave up, concave down, any local extrema or inflection points. These questions are very, in my experience, it's tough for students to know what they need to do to get which information. And in particular, it's sometimes hard for students to know which derivative they need. Like increasing and decreasing and local extrema, this is all first derivative stuff. A function's increasing where the first derivative is positive, it's decreasing where the first derivative is negative. And to find local extrema, what you do is you make a number line for f prime, and a local max is wherever you see a plus followed by a minus, and a local min is wherever you see a minus followed by a plus. And that's the number line for the first derivative that you're looking at for local extrema. This other stuff, concavity, whether it's concave up or concave down, and then inflection points, that's all second derivative stuff. And it's completely analogous to the first derivative stuff. It's just about the second derivative. Concave up is when the second derivative is positive. Concave down is where the second derivative is negative. An inflection point is where, if you draw the number line for the second derivative, an inflection point is where you see a plus followed by a minus, or a minus followed by a plus. They're both called inflection points. Yeah. And that's kind of out of sections 4.3 and 4.5. We went over a lot more than just this information. Like, we did some of those examples that took us, they took us forever, frankly. It took me like a whole class just to get through one, where we found all this information like horizontal asymptotes, vertical asymptotes, and x-intercepts and y-intercepts, and so yeah, I mean, stuff that I'm even forgetting. But we're not going to do all of that. I'm just reminding you that that stuff was in section 4.5. What I'm going to do on the test is ask you for this information. I'm not going to ask you on a single question, because those questions took us forever. If I put a question like that on the test, that would have to be the whole test. So I'm not going to ask you for all of that information about a function. I'm going to ask you for this information. Anyway, moving on. There was also L'Hopital's rule, which is section 4.4, like this one. This is one where, of course, you should start it like any limit, which is just attempting to plug in the number for x. Typically, you'll get 0 over 0 or infinity over infinity. That's kind of what L'Hopital's rule is for. And then what you do is you take the derivative of the top and the derivative of the bottom. You should expect one where you have to do L'Hopital's rule more than once. Like this one. If you try L'Hopital's rule on this one, you should have to do it more than once. Moving on, there are optimization problems. These are also word problems. They tend to have a lot of wordy details, and so I didn't write a specific example, but they're out of section 4.7, and here's some examples if you want to see them. But just to jog your memory, it's these are the ones where you often want to maximize or minimize something. For example, there's several of these where, like, a farmer has to build a fence, and maybe the farmer wants to maximize the amount of area subject to how much the fence costs, and you have various twists, like maybe the fence is up against a river, or maybe different parts of the fence have different prices, or stuff like that. There's also a lot of problems in there about, say, you have a certain amount of material and you want to build a box, and maybe the box doesn't have a top, and again, there can be various twists, like maybe different parts of the box have different requirements, or they cost different amounts, or whatever. Anyway, it's ones like that. And then finally, there's antiderivatives, which is section 4.9. So you should expect one where, like, I give you the derivative or the second derivative of a function, then I ask you to find the original function. And that's done, in this case, I gave you the second derivative, so you'd have to do the antiderivative twice to get the original function. Anyway, Yeah, those are the basic problem types you should expect. So I encourage you to take a look, for many of these problem types, I did provide a specific example. You should think about these because I didn't work them out. And I should say that just because, like, say if you're looking at implicit differentiation and you see how to do this one, I encourage you, of course, to look at more examples of implicit differentiation. Don't assume that just because you can do this one means that you're totally fine on implicit differentiation. But if you try this one and you aren't fine, then maybe pay specific attention to implicit differentiation. That's the intention of this. So of course, I'm going to make some more videos where I actually run through examples like this, but I think this video is probably helpful to help people study.